Hello and welcome to my computer vision series. Today we are going to talk about the new task in computer vision called object detection. We're going to look at a new dataset called CoCo dataset that can be used to train models for object detection. It's also, unlike the previous dataset we looked at, unlike ImageNet, has an active challenge on it. So it still has submissions in 2023. So you can still participate, win some money. So it's all sort of in a very active stage at the moment. Finally, we're going to look at the metric used to compare models in object detection called MAP. First, a reminder on where are we in our progress in the course. So we started with the task of image recognition. So we start with classifying digits with low resolution, simple shapes. Then we discussed what to add to our models to make them better. We discussed convolutions, spatial minimization, residuals, all the other tricks in the deep learning science. And then we trained our own ResNet model on the famous ImageNet dataset to classify images. So ImageNet is now high resolution, a lot of images, 150 gigabytes of data, and we were able to do that. Now we move on to a slightly more challenging task called object detection. That is, apart from saying, what object there is, also say where it is, so to paint the actual bounding box. In addition, now we want to see what will happen if there can be many objects on an image, and so how do we deal with that? Image recognition. We had an image of, say, a dog, and the network outputs that it's a dog. Now, we can also speak about object localization. That is, we still assume that there is just one object and always exactly one on the image. But now, instead of class probabilities, we want to predict the bounding box. And so, formally, we specify the x and y coordinates of the upper left corner of this bounding box, and then height and width of the bounding box. And the reason we are talking about this is that we can take the model from our previous example, the model that predicted class probabilities, and just swap this one final layer that outputs 1,000 number for some classes. We can swap that to just 4 numbers, these ones. So these 4 numbers will correspond to x, y coordinates of the bounding box, and then the height and width. And we also will need to change the loss. So we used to train for cross entropy, that is the measure of how close predicted class probabilities are to the real world. And instead we will use mean squared error loss, which is basically how close the number for the predicted height, for example, is to the real height. And the reason I even talk about this is that, so we can sort of train the model to do that with just a few changes. And the reason that is interesting is that it actually unlocks a lot of potential for computer vision. So, for example, one thing we can do is instead of those bounding boxes, we can instead predict a fixed set of numbers for, say, the coordinates of the eye, of the nose, of different sort of important points in the face, which will give us the sort of head orientation. And that was actually used in many computer vision applications. So, for example, the Snapchat camera that was sadly discontinued this year. So it looked at these sort of important points in your face to determine the head orientation, and then it will draw something like a hat on top of you, for example. So it's already sort of working as a sort of generative model, but it's much simpler than what we have now. What we can also do is predict the pose. That's called pose estimation. So we can say that now we have fixed points for elbows, for hands, for knees, and then we let the model predict these fixed points. And from that, we get the pose of the person on the image. and that we might use for, I don't know, analyzing the soccer strategies, for example. And that will work as long as the number of points we predict is fixed. So our model will only work if we have, say, 12 numbers or 16 numbers. Any number of points fixed in advance, that we can work with. But obviously, to actually train the model like that, we will need to have data. So someone will have to actually go through all the pictures and actually label them with precise coordinates for the pose or for the face and so on. So this is a new task for creating data, and so to work with that, we'll have to start from scratch basically. And now we want to move on to object detection. So object detection is again just drawing a bounding box around an object, but now there can be many objects on an image, or maybe none at all. And so we'll not actually discuss the algorithms used to solve that. That will happen in next videos, but you might have heard of them. Examples would be YOLO, RCNN, or Regional Proposal Network, or DETR. But we will talk about one of the most famous data sets for object detection called CoCo. So first of all, just a quick reminder of what the ImageNet looked like. So it was a huge data set, 1 million images, 150 gigabytes of data, and they looked somewhat like this. So this is actually a subset called Tiny ImageNet on Hugging Face. So it has, these are the classes corresponding to a certain breed of fish, I suppose. And there is a lot of fish. So if we scroll down, we still see fish. On the next page, yep, still fish. And then if we move to the very end, oh, now we have oranges. So ImageNet was sort of focused on the classes instead of the images. So they actually started with just the word classification. That's where they got all the sort of different breeds, all the different types, and so on. And then they tried to find what is called an iconic representation of the object. So in all of these pictures, in most of them at least, the object in question is somewhere in the center. It's really sort of in high scale. It's the main object in the image. And so CoCo tried to fix that. So here is the original paper from CoCo. So apart from now saying that we also want to solve the object detection task, we now also, the images themselves are different. So we can go to the official CoCo dataset page. We can just Google CoCo dataset, and it should be one of the first links. Then I go to Dataset Explore, and it lets me choose the classes that I want to look at. So let's go for person. So the CoCo dataset was built differently. Instead of starting with words and then trying to find iconic representation for these objects, instead we just take random images and then just annotate them. So this is more representative of what an average picture will look like. So for example, in this one, we can see person, but we only just see the legs, which is still not a problem for people to annotate. Here we have some people as well. So in here we just see head and a couple of fingers from some other person. More people. Yeah, here is just a small outline of people, like here, for example. This is really small. So it makes the task more challenging. So if you remember, on the ImageNet, the competition got closed in 2017 because an average model with 95, 98% accuracy was already better on recognizing the images than people. On the CoCo dataset, on the other hand, typical state-of-the-art model is much worse than a 4-year-old can do. So the objects here are much simpler, like person, car, bench, bag, but they are in non-iconic representations. So we can see just a head, or just a few fingers, or just the object can be abstracted by other objects. It can be viewed from a really unusual angle, which is what happens in real life. So it's more realistic. And this dataset is alive and well in 2023. So the challenge is still ongoing. This is the Papers with Code website that shows the history of winning submissions and the sort of improvement of state of the art. And we can see that it just keeps going up and up. But even now in 2023, with the best model known so far, the overall accuracy is still like far from 100%. So it's still a challenging task. Apart from that, the dataset contains the bounding boxes, the object segmentation, so the actual area belonging to every certain object. And in some cases, they also have stuff like pose, estimation, and other sort of localizable information like that. Finally, I want to show you the RoboFlow health check for the dataset. It's a cool tool to sort of analyze different information about the dataset. So here is the class balance, for example. So which objects are the most popular in the dataset? And we can see that person is the most popular, which makes sense for a realistic dataset. But then something like scissors or hairdryer or toaster only have like a bunch of images in the dataset. So the models trained on this dataset will not be as good at detecting these objects, probably. The dataset itself is much smaller than ImageNet. So if we come back here, yeah, so it's only 120K images, so it's like 10 times smaller. The reason being that it's already challenging enough, even with that size, and it is much harder to annotate. So with ImageNet, you just sort of provide one class per image, and that's really easy for a person to do. Just type in, this is a dog, and so on. For bounding boxes and segmentation, you would need to spend some time in the graphical editor to actually draw the bounding boxes, to draw the actual segmentation of the object, and so on. So every image now takes much more time to annotate, but it's still enough to train the proper model. Now, finally, I want to discuss the metric that is used here. So this is called MAP, or multi-average precision. So let's discuss what it is and how to actually compute something like that. What will actually happen when we try to detect objects in this picture? So we might have a correct prediction. So a bounding box that more or less corresponds to the truth and says that it's a sheep. We might have something that is just, false positive in the background, like recognizing that there's something here, for example. Or we might predict a sheep correctly, but the bounding box is a bit off. So we want to have a metric that can be used to compare all existing models on the entire dataset, and that will punish all sorts of mistakes. So just random objects in the background that are not even there, misclassifying objects, not being able to draw the proper bounding box, and so on. So now I will explain how the MAP metric works in a series of steps. So first important detail is called intersection over union. And here is the demonstration on when that might be relevant. So if we look again at this picture of the dog, recall that I said that to train a model to localize, to predict this bounding box, we might look at mean square error loss. So mean square error basically looks at errors, so how far off the size of the bounding box is, like here, and height and width, and the coordinate of the beginning of the upper left corner, and then square this number and compute the sum over all examples. But then, depending on the actual size of the object and its location, that might not be the best representation. Because if we look at the picture to the right, the same sort of offset in the size and coordinate of the bounding box now completely changes the picture. So in this one, the predicted bounding box does not even contain any parts of the object. So it's clearly a much worse mistake. So to deal with that, we introduced the intersection over union. So we have a real bounding box and then a predicted bounding box. We first calculate the intersection, which is this small area here. And then we can compute the union, this area here. And then we compute the ratio of intersection over union. So if the bounding box is not even intersecting the ground truth, the intersection over union or IOU will just be 0. If it does intersect it perfectly, then it will be 1. And so it's considered to be good if it's above 0.6, for example. Apart from errors when predicting a bounding box, we might just plain and simple misclassify an object or detect an object that is not there. And to deal with different errors that might arise from that, we talk about the so-called confusion matrix. So this is a 2x2 matrix. In the top left corner, we have the true positive, so it's a correct prediction. And that is when there was a dog and we correctly predicted and there is a dog. In the down right corner, we have true negative. So there is no dog in the picture and the model correctly predicted that there is no dog. And then in the top right corner, we have false positive. So there is no dog, but the model thought that there is a dog for some reason. And in the bottom left corner, we have false negative. That is when there is a dog, but the model didn't recognize it as a dog. In reality, the model doesn't say explicitly that it's a dog or it's not a dog. Instead, it outputs class probabilities. So for a picture like this, it can say that it's a dog with 64% chance and then a cat with 22% chance. And then we, as researchers, have to come up with a threshold after which we decide that this is the object that we need to be looking at. And depending on how high the threshold is, the rate of true positives and false positives changes. So for example, if we say that the bar is extremely high, like we only look at predictions with above 95% probability, then the model will look at this picture here, and it will not generate a prediction with enough confidence to pass the threshold. So it will be a false negative in this case because there is a dog in the picture, but the model could not correctly identify it. On the other hand, if the threshold is too low, we will correctly identify that it's a dog, but we can say that, oh, well, somewhere here there's a cat as well, which is not there. So if the threshold is too low, we might get some random predictions, some false positives. And so to deal with the quality of the model overall, independent on what threshold should we choose, there is a so-called area under the curve metric. So we plot the curve of true positive versus false positives, and then we compute the area under the curve. So the case when the threshold is extremely high, so we are only considering predictions in which the model is extremely confident, it's going to be this corner. So the model rarely does any object detection, and so because of this, true positive rate is small, but the false positive rate is also small. On the other hand, if the bar is too low, so we are somewhere in this corner, then we did correctly identify all the dogs. So true positive rate is extremely high, but then false positive rate is also high because we classified a lot of extra objects that were not supposed to be there. And so we can say that the classifier is better if the area under the curve is higher. And it will usually look like the curve will be sort of more bent. So it will look something like this. So perfect predictor will look like this, which means that even with extremely high threshold, it already correctly identifies all the dogs, but then doesn't have any false positives. And then just a random predictor will usually have AUC of 0.5, and it corresponds to just diagonal line in here. Now, if we look at both this confusion matrix and AUC and the IOU metric, we might get various types of errors. So first of all, to decide when the bounding box is correct, we are going to choose a certain IOU threshold. So we're going to say that any bounding box that intersects with more than 0.6 with ground truth is going to be correct. So in this case, the bounding box is correct, the class is correct, so it's a true positive. Now in this case, the bounding box is off by a lot, so the IOU is just 0.23, so it's not a correct prediction, that's false positive. And then in this case, there is a dog, but we didn't find it, so it's a false negative. And so what MAP metric does, the main one we use for comparisons on the CoCo dataset, is it iterates over different IOU threshold. So the measure of how well predicted bounding box correspond to the truth over different prediction threshold and over different objects. And then we can count the number of true positives and false positives. So this is an example of how that can go. So we start with a relatively small IOU threshold of 0.5 and a relatively small prediction threshold of 0.3. Now, the model correctly identified all the 5 sheep and the human here, but then it did a sloppy job at predicting the bounding box. However, with such a low IOU threshold of 0.5, we still count that as a success. But it also predicted the extra sheep around here. So this is counted as an error. Now we increase the IOU threshold a little bit, and now the dog is treated as not correctly identified because now this sloppy job at bounding box is no longer above the threshold. And finally, if we increase the prediction threshold a bit, now this random sheep prediction went away, but we also failed to classify this real sheep. So now we have an extra error for sheep number 5. And so iterating like this, we calculate the total number of correct predictions and incorrect predictions, and from there we calculate the average metric. And this metric is used in CoCo dataset. So once again, this is the leaderboard for the dataset. So in 2023, it is still up and running, so you can still do submissions, try and beat the current winner, maybe earn some money and improve the science. So in the next video, we are going to look at these models, at some of them, some of the most important ones. And you can see that the advancement over the last few years was enormous. So it's one of the hottest topics in deep learning at the moment. So once again, in the next video, we are going to discuss one of the actual algorithms for object detection called YOLO. You only look once. That will be able to do something like this. So actually draw these bounding boxes and identify objects where there can be several objects on the same picture. So see you soon.